types of current are used in the heating, cooling, and refrigeration industry: direct current and alternating current. Direct current is the type of power that's generated by batteries. It's used in a variety of applications, including solid-state circuitry. Alternating current is the power that's supplied to our homes through receptacles such as these. Most HVAC equipment utilizes alternating current, so it's important for industry technicians to be familiar with AC theory and application. In this segment of our series, we'll discuss alternating current theory, as well as power distribution and voltage systems. Alternating current, commonly referred to as AC, is an alternating flow of electrons. Electrons flow in one direction and then in the opposite direction at regular intervals. The sine wave is a graphical representation of alternating current, which is produced when a conductor cuts a magnetic field. The magnetic field is located between the north and south poles of the magnets shown at the left of this diagram. When the conductor X is located in the middle of the magnetic field, namely points A and C, the potential will be 0. As the conductor rotates from point A to point B, or from C to D, the potential increases until its maximum is reached. As the conductor rotates from point B to point C, or from D to A, the potential decreases until the level of 0 potential is reached. Once the conductor has made one complete revolution in the magnetic field and has cut through the fields of both the north and south poles, we say that one cycle has been completed. The voltage reached at points B and D is called the peak voltage. As we can see, the voltage that's actually generated varies a great deal from the maximum or peak voltage. The actual effect that this voltage has on a circuit is called the effective voltage. The effective voltage can be found by multiplying the peak voltage by 0.707. For example, if the peak voltage was 100 volts, the effective voltage would be 100 times 0.707, or 70.7 volts. Simply stated, 100 volts of alternating current is equal to 70.7 volts of direct current. All electric meters are calibrated to read effective voltage and amperage. The number of cycles that are completed in 1 second is called the frequency and is measured in hertz. In most areas of the United States, the frequency of AC power is 60 hertz, or 60 cycles per second. Another important factor that characterizes electric power supplies is the phase. The phase of an AC circuit is simply the number of currents that are flowing at different time intervals in the same circuit. This figure represents a single-phase power supply, while the circuit represents three-phase power. When one winding is used to create the stator, or stationary portion of the alternator, single-phase power is generated. When there are 3 separate windings in the stator, three-phase power is generated. From an earlier discussion of Ohm's law, we mentioned that there is a predictable relationship between voltage, current, and resistance. This relationship is somewhat altered when we deal with AC current flowing through circuits that have inductive loads, such as motors or solenoid coils. The changing voltage in an AC circuit leads to changes in the strength of the magnetic field as a result of Ohm's law. These changes in the magnetic field produce a second voltage called induced voltage, which counteracts the effects of the original supply voltage. The supply voltage must first overcome this induced voltage before current can flow. This effect, called inductance, causes a voltage to lead the current because voltage is applied before current can flow in the circuit. In addition, alternating circuits are also affected by the opposition created by the changing of direction of current flow in an AC circuit. This resistance is called inductive reactance. Inductive reactance also causes the voltage to lead the current in AC circuits. In addition to induced voltage, capacitors also have an effect on the relationship between current flow and voltage in AC circuits. Capacitors are designed to store electrons and are commonly found in the circuits that control the operation of electric motors. Capacitors charge and discharge at the same rate as the voltage applied to the circuit. When the supply voltage and the capacitor charge reach zero, there is no opposition to current flow, and the current is therefore at its maximum. This causes the current to lead the voltage. This interaction between current flow and applied voltage is called capacitive reactance. The sum of the circuit resistance, inductive reactance, and the capacitive reactance is called the circuit impedance. Reactance has an effect on the power of the circuit because the voltage and current are not working together. The actual circuit power will be somewhat less than the calculated power. In a circuit with no reactance, the actual power will be equal to the voltage multiplied by the circuit current. If the voltage is 100 volts and the current is 10 amps, the power will be 1,000 watts. However, if there is reactance in the circuit, the actual measured power may be only 900 watts. The ratio of the measured power to the calculated power is called the power factor. Using our previous example, the power factor can be calculated by dividing the measured power of 900 watts by the calculated power of 1,000 watts, given a power factor of 0.9. The closer the power factor is to 1, the more efficiently power is being utilized in the circuit. Alternating current is generated at a power plant and is then distributed to the end users. In this segment, we'll examine different types of voltage systems and how this power reaches those who rely on it. The voltage generated at a power plant is often in the range of 120,000 to 220,000 volts. With the aid of step-down transformers, the voltage is reduced to about 4,800 volts at strategically located substations. This voltage is then supplied to the end users, where it's further reduced to the desired voltage, which is often 120 or 240 volts. Larger industrial and commercial applications require higher voltages. Single-phase alternating current exists in most residences and is the primary power source for most small heating, cooling, and refrigeration systems. Quite often, the single-phase power that's supplied for these applications is 208 to 230 volts. 110 volts, which is commonly found in residences, is made up of one hot wire and a neutral wire that supply 110 volts. The hot wire is often color-coded black and fused, while the neutral wire, which is often connected to ground, is color-coded white and is not fused. The 240-volt single-phase system consists of two hot wires and one ground. Both L1 and L2 are fused, but the ground is not. A voltage reading of 120 volts can be measured from either hot wire to ground. When a voltage reading is taken between L1 and L2, the reading will be in the 240-volt range. Three-phase electrical services supply three hot legs of power to satisfy the needs of many commercial and industrial applications. Three-phase power is configured with three fused hot legs and one ground wire. It's essential for the technician to understand three-phase power supplies because of their versatility and the different voltages that these supplies can provide. Three-phase power can be configured as either a Y or delta system. The three-phase delta configuration is used primarily in structures that require a large number of three-phase power circuits. The secondary winding of the transformer is configured as shown here. The shape of the windings form the Greek letter delta, hence the name. A neutral wire is connected to the middle of one winding. Voltage measurements from either L2 or L3 to neutral will yield readings of 120 volts. A voltage measurement from L1 to neutral, however, will yield a reading ranging from 180 to 208 volts. This reading is higher than the other two because the transformer is a high leg delta. Voltage readings between any two hot legs will produce readings of 240 volts. The L2 or L3 hot legs to neutral can be used to power circuits requiring 120 volt service. Connecting the high leg to a 120 volt appliance can result in damage to the device. The three-phase Y configuration is used primarily in structures that require a large number of single-phase 120 volt circuits. The secondary winding of the transformer is configured as shown here. The shape of the windings form the letter Y, which gives it its name. Like the delta connection, the three hot legs in a Y are also fused, while the neutral is not. A neutral wire is connected to the middle of the Y. Voltage measurements from L1, L2, or L3 to neutral will yield readings of 120 volts. Note that the Y connection has no high leg, which is the main operational difference between the Y connection and the delta connection just discussed. Voltage readings between any two hot legs will produce readings of 208 volts. The three hot legs to neutral can be used to power circuits requiring 120 volt service. The Y connection can be easily identified by either taking voltage readings from all three legs to ground or by checking the voltage between two hot legs. A reading of 208 volts between all legs indicates that the power supply is a Y configuration. In addition to the electrical systems we've just discussed, there are several other power systems that are becoming more popular because of their versatility. These systems include the 240, 480 volt single-phase system, the 240, 416 volt three-phase system, and the 277, 480 volt three-phase system. Just as the other Y configurations, this system is configured with the three windings connected to form the letter Y. The ground wire is connected at the junction of the three windings. Readings from any hot leg to ground will yield a reading of 277 volts. This electrical system cannot supply 120 volts or 240 volts without the use of additional step-down transformers, so care should be taken when connecting devices to these circuits to prevent damage to them. The voltage between any two hot legs will be 480 volts. This type of electrical system can provide 270 volt single phase, 480 volt single phase, or 480 volt three-phase power. The 277 volt system is very popular for use in fluorescent lighting circuits. This type of system can easily be identified with the help of a voltmeter. A voltage reading of 277 volts from a hot leg to ground, or a reading of 480 volts between two hot legs will identify this system as a 277, 480 volt system. Alternating current is an alternating flow of electrons. Electrons flow in one direction and then in the opposite direction at regular intervals. As a conductor moves through a magnetic field, different potentials, or voltages, are generated. The frequency of a system refers to the number of cycles that are completed in 1 second. Inductance is the effect of the changing magnetic fields in AC circuits. This causes a voltage to lead the current. Inductive reactance is a result of the resistance that exists when the electron flow is reversed. Capacitive reactance is present in circuits that contain capacitors. This effect causes the current to lead the voltage. The power factor in an AC circuit can be determined by dividing the measured power by the calculated power. 120-volt single-phase systems use one hot leg and one neutral. 240-volt single-phase systems use 2 hot legs and a ground wire. 3-phase systems use 3 hot legs and a neutral. 3-phase systems can be configured as either a delta or a Y. The delta configuration is identified by the high leg that exists between one hot leg and neutral. This series continues in our next segment on the installation of heating, cooling, and refrigeration systems.